So we're still here on the topic of ionic bonding, but we're going to take a slight turn and talk about metallic bonding. So if ionic bonding is between a metal and a non-metal, metallic bonding is when you have a metal and a metal. And it can either be atoms of the same metal or atoms of different metals. So let's start with a single element metallic structure. And if you have, for instance, copper or silver or iron, the structure of that is held together by what are referred to as metallic bonds. Well, how do metallic bonds work? We know that metals tend to lose their valence electrons, or at the very least, they don't hold them very tightly. And so in a metallic structure, what you have are your metal cations, and the valence electrons that are just not held tightly are able to kind of move around within that structure. So as we look at all of these electrons, they're going to move and flow within this structure in a bunch of different ways until what you get essentially is this flowing kind of sea of electrons which generate a glue that hold these cations together. So it's this like negative glue that doesn't ever really set. And so it allows those cations to slide back and forth past one another because there's always that negative buffer there. We typically refer to those as free floating valence electrons, or sometimes you'll hear them referred to as the electron sea. You can also mix elements that are not the same. And when we have two metals, which are not the same mixed together, we have what are called alloys. And there are many, many, many different examples of alloys, but here are just a couple, maybe common or familiar ones that you would be aware of. So, of course, gold that is used in jewelry has a bunch of different versions. You have 14 karat gold and 18 karat gold and 24 karat gold, all of which are representing different mixtures. Carat weight for gold, or carats as they're used in gold, are parts out of 24. I'm sure there's a history there. I'm not sure what it is, but 24 karat gold just means 24 out of 24 parts are pure gold, whereas 14 karat gold would only be 14 parts gold. And then they're going to mix things in like silver and copper to vary the color and the quality of that metal. And so there are various alloys of gold depending on how much of these other substances are going to be mixed in there. Cast iron is a version of iron that has carbon, silicon, and manganese mixed in small quantities to generate different properties. What that allows for cast iron is it allows it to take very high heat, and so you can use it, for instance, in a frying pan. And then we have brass, which is used for many things, but also in commonly in brass instruments, which is typically an alloy of copper and zinc. There are several different ways to make alloys. So here in the top left corner, we see kind of the pure metal, where it's all a single cation. Again, the red dots there to represent cations, and the free-floating valence electrons would, of course, be in between all of them. A substitutional alloy is going to replace some of those cations in that structure with different metal cations. And again, there are reasons you would want to do this. You might need a metal that's more malleable. It can be shaped easier, but retains some of the strength of the original metal. You may want to increase its ability to absorb heat. You might want to raise the melting point, and so generating an alloy would potentially change that. So there's your pure metal, your substitutional alloy, and then you can have what are called interstitial alloys, where a metal cation would be inserted in between the structures. And then, of course, we can do substitutional and interstitial alloys combined. Again, all of these are slight manipulations to generate different properties to the metals. The list on the left you should already have. This is our list of properties, or at least a partial list of our properties of ionic compounds. And really we just want to compare those to the properties of metals and alloys. On the left we have ionic bonds, on the right we have metallic bonds. Metals are typically are solids at room temperature, much like ionic compounds. They have three primary properties that we assign to them: ductile, malleable, and that they're good conductors of electricity. Again, an ionic compound can conduct when it's in either solution or its liquid form. It's not going to conduct as a solid because there's no way for charge to move around. But because the free-floating valence electrons are free to move throughout the structure, it's really easy to push electrons in and out of a metal. And so they're good conductors of electricity because the electrons can flow freely. Malleability means ability to shape and bend without shattering. And so we'll look at kind of a representation of that in a second. And ductile just means it can be pulled into long, thin wires, which is useful, of course, because we use metal wires to transmit electricity from power plants to relay stations and then eventually to your home. Let's look a little bit at malleability here and why malleability works. So if we look at the image on the left and you give that a good whack with a hammer, you'll move that structure out of shape, and yet the free-floating valence electrons can just move with them, and they still generate that buffer between the positive cations. And so metals can be shaped and bent fairly easily because those free-floating valence electrons allow things to move around. Whereas we look at our ionic solid on the right, if I give that thing a pretty hard whack, I'm going to force two ions next to each other that are the same charge without any kind of barrier in between them. There's nothing keeping those charges from repelling each other fairly strongly, and so you're going to end up with a fracture line where those like charges are attached or are brought near each other. And so that's why we refer to ionic solids as being brittle. If you whack them with a hammer, they're going to shatter. You whack a metal with a hammer, it's going to bend. With respect to representative particles, again, the representative particle of an ionic compound is a formula unit. It's the smallest particle of that compound that retains the properties of that compound. Again, compounds are pure substances. They have chemical formulas. For metallic bonds, it's really not proper to refer to them as compounds. Mixtures of metals are called alloys, or they're elements if it's a pure metal. If it's a pure metal, then of course the representative particle is a single atom. But if it's a mixture, alloys don't have chemical formulas. They are not compounds, they are mixtures. And for instance, if you look at brass, which is copper and zinc, there are all kinds of percentages of copper and zinc. All you have to do is do a little Googling of the properties of brass on Wikipedia, and it will show you 6 or 8 different versions of brass depending on the percentage of copper and zinc. So you might measure an alloy by percent composition, but that's not a chemical formula because it's not fixed, and that can certainly vary. And the last thing we want to look at is strength of bond. In general, ionic bonds are stronger than metallic bonds, and you can see that when you look at the melting points of ionic compounds versus the melting points of pure metals. And so when we look at the melting points of the ionic compounds, 800, 600, 700, 2500, right? Whereas we look at the melting points of metals, tin melts at 232 degrees, lead melts at 327, aluminum melts at 659, and of course, not every metal has a lower melting point than every ionic compound. But if we were to take the average of a bunch of ionic compounds and the average of a bunch of metals, we would find that the metal melting points are lower because in general metallic bonds are weaker than ionic bonds. But again, general trend, not a hard and fast rule.